Okay, Assalamualaikum dan salam sejahtera. Kita sambung sedikit sahaja lagi nota kita. Now we are looking for another question for boundary layer. So estimate the total shear drag on a ship traveling at 10 meter per second if the side are flat plates 10 meters times 100 meters with zero pressure gradient. What is the maximum boundary layer thickness? So in this question, they ask you to calculate about this ship, okay, traveling here, okay, at 10 meter per second, and you know this 10 meter per second is the capital U. And yes, we normally would say that, okay, ship is something like this. If it is too long, so we assume that, okay, it is some kind of curved design here, but actually it can be assumed that it is equal to a flat plate. Okay, it gives you the dimension 10 meter times 100 meters. So I think you could imagine that so if this is the shape, so the length here is 100 meters. So, and then the area here, the depth here is 10 meters. Okay, normally in shape, we assume that the 10 meters here is actually the area, the wetted area, means that the area that are wetted by the water. Okay, so and then what is about the word of zero pressure gradient? Okay, because normally in our definition, we assume that the pressure is constant. So constant mean the pressure is not changed. So if the pressure is not changed, so the pressure gradient is zero. Okay, so that's the basic assumption in a boundary layer. So and then, okay, the discussion first, because we are dealing with ship here, so we assume that the fluid is water. So and then we check the Reynolds number. Okay, because this is a very short question, but you need to very careful. Okay, so normally you need to check the Reynolds number. So please remember the equation of Reynolds number. So I use rho ux over mu. I substitute all the parameters here. And in this question, we are dealing with water. So you should know, you should remember the density of water, the mu of water, and also the nu of water. Because normally in fluid mechanics too, if we deal with a common fluid, which is water and air, so the properties of water and air will not be given in question because it's a very common, and we hope you remember that parameter. So I take the simple one. So 1000 for density, 1000 kilogram per meter cube, and 0.001 for mu here. So this is the speed, 10 meter per second, and the 100 is the length. So I found that the Reynolds number is 1 times 10 to the power of 9. So I could assume that it is fully turbulent. So and then normally with this high Reynolds number, so the length of lamina is actually very, very small. So you may calculate that lamina turbulent. So normally we could ignore the lamina boundary layer. So let's say we assume it is fully turbulent. So and then because we don't have any velocity profile here, so we could make assumption by using this table. So I think in my notes and also in textbook, you could see this table, this range. So if it is less than 0.10 to the power of 7, so we will use 7, or 8 here, we use 8, and 9 here is 9. But if you see carefully the range here, it is between 10 to the power of 8 to 10 to the power of 9. So in our situation here, we just have the maximum limit of this one. Okay, we have the maximum limit of this one. So that's why, okay, I assume that the Reynolds number is too large. So I assume that it is not proper to solve this problem by using the power law form. Okay, please remember that in turbulent, so we have two methods. One is power law form and another one is the empirical form. So because the range here, okay, is very large now, so I consider to solve this problem by using the empirical form. So you may see textbook page 398. Okay, we also discussed this in previous notes and in previous lecture. So first, we could calculate the value of CD. Okay, so the value of CD here is 0.523 over ln in bracket 0.06 Reynolds number square. So and then if we substitute the value of Reynolds number, we could get the value of CD. It is around 0.00163. So and then if we calculate the value of drag force here, so this is the equation of the drag force. So FD is equal to CD times 1 over 2 rho AU square. So we could get it is 81,500 Newton. But be careful because this calculation is actually based on single side, on one side. Because in ship design, we have two surface here. So we need to multiply this one into multiply with 2. So we could get the total drag force. It is equal 163,000 Newton. So and then if you want to calculate the boundary layer thickness, okay, so first, okay, so we need to use this equation. Okay, you could refer to our previous lecture. So I show you a few examples using this. So according to this equation, we need to know what is the value of U tau here, and also what is the value of, okay, so we need to calculate the value of U tau here. So how to calculate the U tau? Okay, so the U tau here, so we need to calculate the value of, okay, first, okay. Okay, so to calculate the value of U tau, okay, so we need to calculate the value of tau naught. So the equation for tau naught here is given here. Okay, however, the equation of tau naught is conclude of this one. This one is actually the value of CD. Okay, so we start to calculate the value of C small d here, means the local drag coefficient. So we are using 0.455. So we substitute the value of Reynolds number here. So we get it is around 0.00142. So and then, so we use this value, we substitute it here. So and then we calculate, we could get it is around 71 Pascal. So and then by using 71 Pascal here, so we could calculate the U tau here. So we get it is around 0.2665 meter per second. So and then we use the value of U tau here, okay, to calculate the value of delta. Because here is the kinematic viscosity. So this is the kinematic viscosity. So and then this is the U tau again. So this is the free stream velocity. So free stream velocity, it is in this question, it is equal to 10 meter per second. Okay, means that all the parameter is there. You could calculate and then you could define as delta is equal 0.89 meters.